Okay, guys, this is the third example, third part of our video lecture series for integrals of transcendental function. Okay, we are left with the example that was presented in the second video lecture on example number 2. So you have the integral of x squared plus 2 over x plus 1 dx. This is this is for definite integral to be evaluated from 0 to 2. Okay, it was suggested in the previous video lecture that you will be choosing the representation of x squared plus 2 as u, but actually what is presented here is a different technique. Okay, so uh, the technique here is that we need to realize that the expression x squared over plus 2 over x plus 1 is in the form of an improper fraction. So an improper fraction is a fraction whose numerator is greater than the denominator. So for cases wherein the given expression is an improper fraction, we could actually do an expansion of the fraction into its quotient form, just like what we see here, that x squared plus 2 over x plus 1 was divided between the x squared plus 2 was divided by x plus 1, so that you will have the expanded quotient as x minus 1 plus 3 over x plus 1. Now, if you're not able to get how this expression was derived from this one, you do the manual division of x squared plus 2 over x plus 1, so that you will have this one. Of course, this is the result of the main quotient, and 3 over x plus 1 would be the remainder. Okay, so I will not be discussing further the process of the long division here. I am suggesting that you do the long division yourself. Okay, so I'm doing what I'm presenting here is simply the process of the integration. Okay, so once you are done with the expanded form or the quotient form of the division of the improper fraction, then you replace the original expression with the expanded form. So what we notice here is that the new integrand would be is comprised of several terms. So just like what we have discussed in the properties of the integral, we can actually distribute both the integral sign and dx to all the terms within the algebraic expression, so that we can have integral of x dx, integral of negative dx, and integral of 3 integral of dx over x plus 1. Okay, so I'll be presenting to you the solution for this one. This is example number Okay, so this is example number 4 in this Word document. Okay, so this is the same given as presented in the PDF document a while ago. Okay, so this is the part wherein we have replaced the expression x squared plus 2 over x plus 1 by the expanded quotient form. And this is the distribution of the integral sign and dx to all the terms within the expression. Now the next step here is to perform the integration or the antiderivative of the given expression in each of the integrals. Okay, so of course we will be using the power formula here in the first integral, so that would be 1/2 x squared. As for the second term, we have negative integral of dx, so that is simply negative x. And of course, the third one is try to notice that this is in fraction form. What the technique here is to let u equal to x plus 1, then you get du as equal to dx. So therefore, this is in the form of du over u. And we know at the very first introduction of this video lecture series, part 1, du over u is equal to ln of u then plus c. So that means we have 3 ln of x plus 1, but we do not attach the plus c constant because this is a definite integral. So we will be evaluating the resulting integral from 0 to 2. Okay, so this is the result of the integration. Now, the next step is to substitute the value of the upper maxima minus the lower minima. Okay, so we have the substitution of 2. So we have 1/2 2 squared minus 2 plus 3 ln of 2 plus 1. minus the substitution of the minima. So we have negative 1 half 0 square minus 0 plus 3 ln of 2 plus 1. Okay, so of course this is 2 square. 4 divided by 2 gives you 2. 2 minus 2 gives you 0. As for this part, this is 2 plus 1, this is 3. So we have 3 ln of 3. Now, for the rest of the result, of course, multiplication of 0 becomes 0. So 0, 0. This becomes 2 plus 1 gives us 3. Okay, so this is 3. Next would be, we have 2 minus 2 is 0, 3 ln of 3 minus 3 ln of 3. Okay, so let me just okay, so this becomes 1. Okay, so 3 ln of 0 plus 1 for the substitution, and then this becomes 3 ln of 1. And what happens here is that this becomes 3 ln of 3 minus 3 ln of 1. Now, 3 here is a common term, so we can factor that out. So what is left here is 3 ln of 3 minus ln of 1, which can be converted into ln of 3 over 1 by the properties of the logarithm. If you do not know, if you cannot recall this properties of logarithm, you could probably review your basic trigonometry or your differential calculus. Okay, so 3 ln of 3 over 1 becomes ln of 3. Now, of course, we can convert this into exponential form, or into an exponent. We can induce put the 3 here as the exponent of 3, so we can have ln of 27. Okay. Okay, so I'll be discussing last two examples for this video lecture series. Okay, so we have the integral of tangent x dx as one of the integral of the rest of the trigonometric functions that we have. Of course, we know that the derivative of sine is cosine. Therefore, the integral of cosine is sine. The derivative of cosine is negative sine. So, therefore, the integral of sine is negative cosine. I also, in this document, I also summarized the corresponding formulas for those derivatives that are needed. So the derivative of sine is cosine, the derivative of cosine is negative sine. Also, from your differential calculus, you should be able to get from your notes the other derivatives for the other four trigonometric functions. So, for example, we have the derivative of tangent x. We have secant square x dx. The derivative of cotangent x, we have negative cosecant square x dx. The derivative of secant x is secant x tangent x dx. And finally, the derivative of cosecant x is negative cosecant x cotangent x. Now, I'm discussing this set of derivatives because it is part of the transcendental function. The trigonometric functions are part of the so-called transcendental functions. So, of course, since we have the integral of we have the derivative of sine and cosine, so therefore we can also have the integral of cosine equal to sine. So okay, so wait, let me just include the formula for the known trigonometric functions in our list. So if we're going to reverse this process, so for example, the derivative of sine x is equal to cosine x derivative of x. So we have dx. So if we're going to reverse this, we should be able to have the integral of, okay, so integral of cosine x, we should have so we should have sine x then plus c. Okay, so doing the same for sine instead of cosine, so we have integral of sine x dx. We should have this should be negative cosine x then plus c. Okay, so in our list of integrals, derivatives, we have derivative of sine x is equal to cosine x, derivative of cosine x, negative sine x. So it means that if we're going to integrate also secant square x, we should have tangent x. Okay, so doing the reverse for this one, this should be okay. So let me just do this for the other four. So if we're going to have okay, so if we're going to reverse what we have seen in the list of derivatives, the integral of secant square x dx should give us this should be okay. So this should be tangent x. Okay, so the next one is if we're going to get the derivative of the integral of cosecant square x dx, this should be equal to negative cotangent x then plus c. Okay, so for the last two, we have the integral of secant x, the derivative of secant x is secant x tangent x. So therefore, if we're going to reverse the process, we're going to integrate secant x tangent x, we should get secant x. Okay, so I'll be including that in the list. So we have secant x tangent x dx. So the integral of secant x tangent x dx should give us, this should be secant x then plus c. Okay, so last of the in our list would be the integral of cosecant x cotangent x dx. This should give us the value cosecant x and negative. Okay, so this would complete the list of integrals that for this topic, the list of derivatives and the list of integrals. Okay, so let's proceed with the example. Integral of tangent x. Try to notice that the integral of tangent x dx is not included in this list. It is not included here. So since we already have the form of integral of cosine, we have the form of the integral of sine, it is but logical that we naturally look for the form of the integral of tangent x, integral of secant x, integral of cosecant x, integral of cosecant x. Okay, so let's start now with the just to complete the list. Okay, so let's start with the integral of tangent x. Okay, so before we proceed, we take note that in our trigonometry, we know that tangent is equal to the ratio of sine over cosine. Okay, so we have sine over cosine. So if we're going to replace tangent x with sine over cosine, we will have this we will have this form of the integrand. Now, if we let u equal to cosine x, and we get du, the derivative of cosine is negative sine x dx. Therefore, we can replace sine x dx in our numerator here as equal to negative du. Thus, our original representation for the tangent x, which is sine x over x, is can be written as negative du over u, or negative integral of du over u, and of course, integral of du over u is ln u. Or since that is negative, that would be negative ln u plus c. Or of course, this is negative 1. We could place our negative 1 as an exponent for our u as part of the property of the natural logarithm or the logarithms. We have ln of u raised to negative 1 then plus c. Of course, u raised to negative 1 is can be reciprocated so that we have 1 over u. And of course, by resubstituting the value for u. Our original u is equal to cosine x. Therefore, we have 1 over cosine x. Now, recall also that part of the trigonometric identities, 1 over cosine x is secant x. So, therefore, we arrive with the integral of tangent x dx as equal to ln of secant x then plus c. Okay, so next would be the integral of secant x dx. Okay, so in order for us to perform the integral for secant x dx, we take note first of the following. I have listed in our list of derivatives the derivative of tangent. Recall that the derivative of tangent is secant square x dx, and the derivative of secant is secant x tangent x dx. Now from this, note that if we're going to add the two derivatives, derivative of tangent plus the derivative of secant, as you can see here, the result would be secant square x dx plus the result secant x tangent x. Secant x here is a common term. We could actually factor that out. So we can have secant x times secant x plus tangent x dx. Now, taking note of this result, we can therefore, as part of our technique, this is actually a technique, take note, if we're going to introduce the term secant x plus tangent x over secant x plus tangent x in the integrand, our original secant x dx becomes secant x times the introduced term. Now remember that this is to maintain equality. Still, the overall value of this integrand is still equal to secant x. Why is it that this is still equal to secant x? It is because what we have introduced here is actually still equal to 1. So remember, this is a fraction, and if we're going to divide a fraction with a term such as 3 divided by 3, that is equal to 1. So since the numerator is the same as the denominator, this is actually equal to 1. So that means even though we have introduced this factor inside our integrand, we also maintain the equality of our integrand from our original, since this value is just equal to 1. But we need to introduce the idea of the term secant x plus tangent x because of this result. Otherwise, if we're not going to introduce this, we will not be able to use the standard formulas that were introduced a while ago. Remember that this is a technique. Okay. Okay. So we're already in this part. So next step is to distribute secant x to the numerator. So we have secant x square, or secant square x plus secant x tangent x. Notice that we already have this term in our previous sum of derivatives. Secant square x dx, secant x plus tangent x. Now, if we're going to let u equal to secant x plus tangent x, du would be equal to, of course, if you're going to have the derivative of secant x is secant x tangent x. The derivative of tangent x is secant square x. So therefore, this is your du, which is the term that appears here in the numerator. Replacing that with du, our original form of the integrand becomes simply integral of du over u, which is of course integrated into ln u then plus c. Replacing u with the original representation, our u is equal to secant x plus tangent x. So therefore, we have ln of secant x then plus tangent x then plus c. That is the result for the integral of secant x dx. Okay, so we have now 4 of the trigonometric functions in our list. We have the integral of sine as cosine in our list. In our list of integrals, so we have integral of cosine x as equal to sine x dx. Integral of sine x is equal to negative cosine x. Okay, so we could actually complete the set here if we're going to write that down. Okay, so let me just add these in the or probably you could be the one who would add up to just add the result to the list. So you have the integral of tangent x dx as ln of x ln plus c. Then you have the integral of secant x dx ln of secant x plus tangent x ln plus c. Now what is left in the list is the integral for cotangent x and the integral of cosecant x. Now these two will be left as an assignment for you to do. So I am expecting that you will be submitting the assignment on Monday. That would be on May 2. Okay? So, included in the previous mentioned exercise that was mentioned in part 1 of this video lecture series. Okay, so as a suggestion, you could pattern the solution for getting the integral of cotangent x and the integral of cosecant x with the presented solution here in number 6 and in number 5. So just replace integral of tangent with integral of cotangent. Take note that cotangent is cosine over sine, and then you proceed further down. As for integral of secant, you could replace this by integral of cosecant x, and take note that the derivative of cotangent is negative cosecant square. The derivative of cosecant x is negative cosecant x cotangent x. Then you add, then you introduce, then you follow on with what terms should be introduced and so on. Okay, so this is your assignment. I am expecting, again, this will be submitted on Monday, May 2. And also take note that I already mentioned in one of my emails that what I'm asking you as part of the submission is that your solution should be handwritten, it should be scanned, and it should be sent to me through email in JPEG format. Okay?